Where's that? Oh! Oh, Trev's going! He's heading for the creek!
What trouble can we get into today? It is fun time sunshine, because on this lecture we are talking about the incline plane, and this is of course in relation to a force table. And when it comes to the incline plane, we're going to find out there is a quirk. There is a is it mathematical or mathematical? I don't know, let's say a mathematical. I don't think that's right, but I can't spell it. All right, so let's just go mathematical quirk. And I also like to call it the bitter pill. I think Grandma and Jake always used to talk about the bitter pill to swallow. It's a bitter pill to swallow, but it'll make you stronger in the long run. So a quirk, bitter pill, to make problem easier. There's going to be a quirk here. Not a lot of folks are, if you haven't seen it before, you don't exactly like it the first time out, but just bear with me. It makes the math easier. All right, cool. So for the inclined plane, I'll somewhat introduce it the normal standard way. Won't solve it because it just gets so painful. And then I go back my merry way. Maybe I'll stick in one where I solve it actually all the way. That's just going to add 20 minutes of the video. And I don't know if your popcorn will last that long. All right, so there's two methods, all right? And it comes down to the old way, the ways of the old days, which was yesterday or a few minutes ago, and the way to get around this, to use this this quirk in order to make things easier. So remember, the first method is the normal way. If you've never had physics before, this is what you'd be considered to do. Hey, you know what? We've done force tables before. We've been doing several already up to this point. You just have the X, Y axes as before, with X being horizontal and the Y being the vertical. No problem there. And you could solve it. It's not unsolvable. But lots of terms. Okay, lots of angles too. A lot of different angles. You gotta keep track of them all. It's not saying the new way is not going to have any angles. It's just that there's usually far fewer of them. So what do we do in the new way? a new way, we're going to have a new XY axis. The XY axis has to be perpendicular to each other, so that will be maintained. We're going to rotate it. And if you're in math, rotations can be done with matrices and stuff like that. It's really cool. We're not going to do that. We're just going to rotate it, and then we're just going to define that's my new x-axis. And here we go. There's nothing in the Constitution that says the x-axis has to be horizontal and the y-axis has to be vertical. It's not in the Constitution either, but what mathematically must be maintained is that these two axes are perpendicular to each other. So anything you can have, that's the only thing you need, it's the only requirement. You can draw the x-axis, you can draw it horizontally, you can draw it weird. People even in this class have drawn the x-axis as the y-axis, and that gets a little bit hairy for me when I grade stuff. Like, I got one of these x-y axes people flipping. All right, but it's okay. It keeps me on my toes. I'd rather for you not to keep me on my toes. All right, just stay on target. That's it. Stay on target. Stay on target. You folks out there probably don't know where that line's from. So a few mysteries in life never hurt you. So we have in this new XY axis where we're going to rotate it. There's got to be some reason we're going to do this crazy thing. And the reason is we're going to have fewer terms. But unfortunately, there's a quirk. Okay, so let's begin. Suppose you have a 50, not 550, put a little decimal there to make it look like more sig figs, 50 kilogram mass setting on a frictionless incline. Now it's frictionless right now. We haven't introduced friction, but if you were in Illinois right now, you'd be able to look at that horizon in the west, or I guess in the east, that's where the sun's coming up, and you'd be able to see friction quickly coming over the horizon for us. So that's one of our next topics. And this just makes this problem even messier if we keep the old way, if we don't rotate the axes. Right? But right now we're just going to keep it simple like this, and still it's going to get a little, it should get a little, obviously get a little hairy for us. So we're on this frictionless incline, but we're going to have somebody pulling on the mass. So a person pulls on the mass with a force. Maybe they're pulling on a handle, it's on the mass. Maybe they're pulling on a rope, and via tension force it's being conveyed to the mass, but it doesn't matter. In the long run, they are pulling on the mass with a force F of 100 newtons. And they're doing it up the incline. And of course, another word for an incline is a ramp. Or also it could be like a slide, straight slide. This is why this problem actually is very, very useful. I mean, we deal with inclines, ramps, slides, even a, not a straight hill, well, a road going up a steep hill, which is nice and level, also would have this applied to it. So this has got a lot of applications in the real world. So we get this person having or pulling up with 100 Newton force, and we'd like to find the acceleration of the mass, of course, up the ramp. Who knows? Maybe it goes down the ramp. I don't know. We'll figure out. There's my, it says it's going to happen, but it doesn't mean it. We'll let the math handle it for us and figure out what's going to happen as far as actual case. Let's see. So can I fit that on there? Yes. I can, but it's a little squished. So let's just move to a different page. Uh-oh. Trying to find a meter stick. Ha! Of course I didn't find a meter stick. I found a ruler, straight edge. Let's draw what this thing's actually looking like here. my angle's most likely way off. Yeah, it's not way off, but it's close enough to me and say it's off. This is a 30-degree angle. That wasn't given in the problem, but you got to kind of, sometimes it is, and sometimes there's a drawing provided and an angle stuck down there. But we like to know, of course, how much of an incline we have. We have an incline which is 30 degrees. And here's yonder mass sitting here. And of course, at this point, before we get to that point, let's write down the information I have. I'm going to lose it because I flipped the page. The mass was 50.0 kilograms. And I can draw that on there about how much the person's pulling. But since this was the first time I referenced this angle, that's the angle of incline. Angle of inclination, angle of incline. Some similar words saying that in a problem, that's what they mean. All right, so here we have a mass sitting there. Well, what have we been doing? We sit there and we sigh, and then we think, you know what, next step is, if I want to find the acceleration of this object, I've got to find F net. And to find F net, I've got to find all the forces acting on my mass. All right, well, they mentioned this thing about this person, for whatever reason, nothing better to do, pulling on the mass with a force. And I called that F, and it was 100 newtons. Okay. Is that it? No. This is when we'd be in class. I'd say, hey, what other forces are acting on it? And the quick person who's awake in the class quickly says, weight. This mass has weight. It does. Anytime you got a mass, you have N times G, that's your weight. And which way is it directed? It's directed always vertically down towards the center of the earth. I should say that. So like that. FG, which looks like it's called W, mass times G. And that's just the magnitude of it. I'm not going to put the negative J at because I'm going to be playing around with that axis, but that's the magnitude of my forces. First step is just to get the forces right and then get those angles, because I got to break them down into components. Obviously, I've got to be thinking components somewhere, because this F and this force, this weight, gravitational weight, definitely does not point along the same axes. Is that it? Nope. This thing is sitting on a surface, and when a mass is on a surface, it has a normal force. Ooh, man, I got arrows pointing all over the place now. And that's the whole problem I've got. All right, so what do we got? Well, that's it. If there was friction here, I'd have to worry about that. Could easily be another person pulling up. Who knows? But right now, I just have three forces acting on it. And with that said, once I got, okay, now I'd like to break my my forces into their components. Right? For one thing, what angles do we have here? Now let's talk about the components here first, and then we'll worry about the components, get the angles. Let's just do a little checklist here. I'm trying to make the case for why we're going to have to rotate that axis. That's what I'm doing here. So you don't have to do this. This is just me saying, hey, there's a bitter pill we got to swallow. This is why. Consider the non-zero components. And angles for our three forces. And that's however many forces there are acting on this mass. In this case, there's only three. Let's put a big gap here. Go. No, farther over there. Okay. How many lines can I draw? That's not my objective. My objective is to make a little division between these guys and that down here, which you'll see. Because why this is, I'm going to label this column as force. And this is going to be, just write Fx on the force. And I guess may I, how about X component? Here we go. I'm gonna make another column right here. Make it audible here. Should be kind of obvious from how I'm going to draw this, but let's say non-zero. Non-zero X component. Let's make a gap here. Non-zero X components. Here's my Y components, my forces, and then non-zero Y component. All right, so what's my forces? Well, I've got the F equals 100 Newton force. Okay, so what's my X component? Well, I have to know the angle that this force makes. Let's grab a red pen. Relative to the x-axis. Now the x-axis, like where's the x-axis? The x-axis right now, that's traditionally drawn, is a horizontal line. So wherever the tail of that vector is, I draw a horizontal line. And this will tell me that angle I need. So that's theta F. What is theta F? Well, if you get in a little geometry here, I have two parallel lines. This base of the incline is, I didn't state that, but I guess the base of the incline is horizontal. So I have two horizontal lines intersected by a transverse line. I think that's the fancy word for it. So this angle right here and this angle is 30. And this, so in other words, this angle is also 30. So theta F is 150 degrees. Right? So I'll know the X component and the Y component for my this person's force of 100 newtons. It's 100 cosine 150. It's 100 sine 150. Definitely non-zero. Definitely non-zero for X and Y's. All right, what do we got next? How about the normal force? Okay. The normal force is perpendicular to the surface. This surface is inclined, so it's not going to be vertically straight up anymore. It's off at an angle, as depicted here by this excellent drawing I've done. So if you could take the normal force all in, it's 9 degrees like that. But I want to know the angle the normal force makes relative to that red line. That's my horizontal x-axis. This is theta n. Oh, what is theta n? Well, if this angle is 30, I wish I'd drawn the m as a little bitty point to be more obvious, but this angle right here is 30. So 30 plus theta n is they're complementary angles. I think if I got that correct, they add up to 90. It's what they should do. So this guy here is going to be 60 degrees. Ta-da. So I've got, I don't know what Fn is. I figure that out, but I do know I got Fn cosine 60, Fn sine 60, and they're definitely non-zero. And my last force I have is the weight. And the weight makes an angle of theta W. I'll just call it theta G. Let me get away with that one. I like that. 270 degrees. So this would be mg cosine 270. And you crank that in your calculator and you find out the cosine 270 is a 0. So haha, I've got a 0. Yippee. There's no check there on that one. And this guy here would be mg sine 270. And that just equals negative mg. But it is definitely non-zero. Okay. So I've got 3 forces, 5 non-zero components, basic case. I guess the most basic case, there's no person pulling up the ramp, I guess, and then, but that's not a very interesting case. It's useful, will the object roll down a ramp if I just sit up there? That's neat, but of course that's going to deal with friction, and hey, you got to bring in the frictional force, which would kind of replace that force right there. So this is the probably your basic generic forces on an inclined plane, and I got a lot of components with lots of different angles, and you might be sitting there thinking, boy, how do you get to 60? Or yeah, there's a lot of angles here. Right? And why the division here? I'm going to add up the sum of the forces in the x direction. I'm going to add the sum of the forces in the y direction. It's going to give me ax, and it's also going to give me ay. So the acceleration will have an x component, which if you add these guys up, there's no guarantee. You might get like it might equal 0, but it's probably not going to equal 0. It just have to be excellently balanced. And you can imagine most times, person can pull easily harder up the ramp, and it's just going to make it accelerate faster up, or maybe slide down if they're being overwhelmed by the normal force of your weight. And your ay is also non-zero. Right? Like I said, there's a chance it's going to be that way. But if this object is moving up or down the ramp, then it is, unless it's going at a constant speed. But if it is accelerating, if this person is making the mass go faster up the ramp, then there would be an x component and a y component of acceleration. Okay. So this thing is really, really busy for us as far as solving it. And like I said, this was considering this. So how we'd solve the for AX, as we will solve no matter what, via the good old sum of the forces in the x direction equals mass times acceleration in the x direction, and also solve for the AY, and that we would sum up this column right here, and that would lead us to getting to AY. Wouldn't it be nice if we can eliminate some of these terms? And how do we do that? I know how we can do that. We can rotate the coordinate system. Let's see. That page was 4. How can we make it easier? Well, also in that last one, I also have the normal forces also an unknown, which wasn't going to be easy to find because it has a component in both x's and y's. Wouldn't it be great if it was just in one of them? We'd be able to solve a lot faster. So how can we make the problem easier? And that's less terms, and the fewer terms you got, probably the fewer angles you're going to have to worry about. And here comes your bitter pill to swallow. And this is only for the inclined plane. We rotate the XY axes such that positive x points along the ramp, or actually, if you can make a good enough stab at it, such that positive x points along ramp in direction of motion. So this part is nice if we can figure it out, but this part is required. The bitter pill is to rotate the axis of the positive x-axis points along the ramp. If we can figure out the direction of motion off the top of our head or just get lucky, then so be it. Our acceleration will be positive. We like positive numbers. If not, acceleration is negative. No big deal. Yeah. I guess wrong. Who cares? We definitely can still figure out which way the thing is sliding. So just redrawing it again. So I redraw the forces. They don't change. They can care less which way my axis is. They act as they act. Kind of draw along the same point. Makes it easier for us to kind of see the angles if we need to. 100 Newton guy. And I don't think I've said it enough, or maybe not said it at all, but we treat all masses as point particles in this unit up until, boy, when we get to torques. When we get to torques, we got to figure out the physical size of an object. But right now, even though you draw a mass, the mass is definitely not a point, but we act like it is. All forces are acting on the point-like mass, so they're acting at the same spot. Otherwise, you can say, well, wouldn't it tip over? Yeah, it probably would in life, but you try not to when you pull it. And so that would pretty much, you mimic what we're trying to emulate here with simpler math. Now, which way should I make that positive x-axis? Okay, well, I definitely want to make along the incline according to this new bitter pill. But the question is, think about if this person wasn't acting on it at all, what would the mass do? It may sit still if there's friction, but for icy, what would it do? It would slide down because the weight would bring it sliding down the incline. So the question is, does this 100 Newton force guy, is this force capable of offsetting the weight pulling it down? Let's be hopeful. And actually, I'm going to guess wrong here. I say, oh, you got to guess this, direction of motion. I don't know. Who's going to win? You can do a quick calculation when you get used to it. But let's just put positive x going up the ramp. Pretty sure the answer is going to be going down the ramp, but it's okay. We'll just have a negative number. No problem. There's my new x-axis. Now, by mathematical constitutional law, my y-axis has got to be perpendicular to this x at all times for the Cartesian coordinate system. So it's pointing that direction. And I mean, we could have chose it going the other way, 180 degrees, but we like to draw it positive. Why? Because you might notice this line here looks a lot like the direction of that, and that's exactly what we're gunning for. The y-axis, if your x-axis is along the ramp, your y-axis, if it's perpendicular, has to be perpendicular to the ramp, or basically perpendicular to the surface the mass is on, and that's the definition of a normal force, perpendicular to the surface the mass is on. So now, really fast, you can maybe see what's going to happen. The normal force no longer will have an x component in this new system. It will only have a y component. Woohoo! And matter of fact, you can see what's going to happen too. Our force for pulling along the ramp, and let's face it, when you pull along a ramp, you don't have to. I could come in here and push along this angle, and I got to live with some hard algebra there and a few more angles. But most of us would pull up the ramp or pull down the ramp, and friction will always act along the ramp. So for usually, in most cases, forces acting on the mass that aren't the normal force or the weight will be directed along the ramp. So they will only have x components and no y components in this new system, whereas in this system they have both. And the angles are becoming like 0 and 90 degrees. I like those. Oh yeah, I can deal with 0, 90, 270, 180 all day long. We all know those are going to be like zeros and ones or negative ones for sines and cosines. All right, so and I can't still illustrate this enough. I just want to put the point. Note the positive y-axis is perpendicular to, looks like plus 0, to a positive x-axis, which means it's perpendicular to the ramp's surface. And that's what we're gunning for. So I'm going to redo that little chart I had before showing the components of my forces. See which ones survive. So let's redo the previous table for the new orientation. Yeah. first. I draw the lines are never long enough or short enough, too long or too short, blah, blah, blah. Let's just draw, are they zero or are they non-zero? Make these lines in red, maybe I'll make it even. I hate to have a table with forces in the left column, something to change what that left column is, but you know, I like to illustrate the point here that what happens to your acceleration. So here's the force. Here's F equals 100 newtons. And I want to know, is the X component not equal to 0? If it equals 0, that's great. I'll put a 0 in there. If it's not equal to 0, I got to worry about calculating it up. So for the 100 Newton force, one at a time. Mass. Positive X. Positive Y. It's paper all over the place. I need a clamp to keep it in place. There's the force of 100 newtons. So, is there an X component? You bet. It's 100 newtons. Is there a Y component? No, it's 0. No Y component. F is completely along the new X axis. So, how about our normal force? I'll redraw the whole thing. Okay, one at a time. I mean, force table, you just have one force table. I'm trying to make a point here. What am I doing on that one? Get back. Okay. I mean, I can't tell you enough. Do not do this on a force table. You draw one table, all the forces are on it. Well, I guess you can. I guess, yeah, I'm thinking about it. You know, it gets just saves room, but I just think it's getting really messy. Then you got to keep track of all your tables, all your different drawings. Don't forget to draw them. So here's my normal force, which by definition is perpendicular to the surface. And hopefully I did a good, decent job drawing that positive Y perpendicular to the X, which should be parallel. And the X should parallel the surface, makes positive Y perpendicular to it. So the normal force has zilcho X component, and it does have a Y component. Matter of fact, that Y component is F sub n. All right, so far so good. Okay, kind of a crazy thing here, but everything seems to be working out just peachy keen. And here's where the bitter pill really gets, got to pay for it eventually. But it's constant. Once we do this once and get used to it, we're okay with this, I hope. Or if not, you just imitate this. Just imitate. Life imitates art, or vice versa. So you say this is the way it works out, and set positive X. Y. Here's my mass. And here is my weight. mg. And mg is still, if I call it vertical, that's fine, but no longer is parallel to the y-axis. The y-axis points to some weird angle. So mg has an X component and it has a Y component. And it doesn't look like there's a big payoff here for this trouble. We now have 4 non-zero components versus the last time we had 5. But these two, but we only have one, excuse me, we only have one force, which actually has non-zero components. And the other guys is either completely along the X, completely along the Y, makes them easier to figure out. So when we add this guy up, we find out that AX will not equal 0. I mean, unless we stand off, unless these two guys completely cancel each other out, the object will have an acceleration up and down that ramp. So there'll be some kind of acceleration up or down. You can change F where you get to that magical spot, the sweet spot where it's just not moving, it's moving at a constant speed, which means no acceleration. But you can imagine mg always stays the same for your mass. So depending upon the person, just, increasing the force or decreasing the force is going to definitely lead to a non-zero acceleration. How about the Y? You might think, well, there's 2 check marks here, and that's non-zero. I just made that case. The Y obviously has got 2 checks, so they must also be non-zero. And no, it's definitely 0 now. The mass is sliding up or down the incline. It's not popping off the incline. It's not going into the incline, and that's the direction of the Y-axis. So the way we've drawn it now, this new axis, I mean, yeah, you could say maybe there's another person pulling with enough force and it's going to rip the mass off the incline. Of course we can do that, but we're not going to. We're just trying to find the motion of an object along an incline, sliding up or down it. I mean, there's a lot of practical use right there. We don't have to add some crazy caveat where we have to worry about springing off the incline. We don't want it to spring off the incline. I mean, something goes down the hill, we don't want you to be pulling it so much where it pops off the hill or ramp. Then the thing's going to start swinging wildly, and that's dangerous. All right, so we don't do those kind of problems, and I hope you keep that in mind when your engineering careers, your careers out there. So based on this new orientation of our axes, AY has got to equal 0. Bonus, bonus, bonus right there. Matter of fact, really fast, I now know what the normal force is. The normal force equals the Y component of my weight. In this scenario, now if there's more force, I got to worry about that, but I can quickly set this guy equal to 0 and find my normal force, which at the point at the previous one was a little bit of problems for me as far as worried about that. And why all the red lines, remember this is for the acceleration. This is, I write it out as AX, not F or anything like that, but these shouldn't technically have been anywhere close on a force table. If I draw these 3 red lines, and I guess we all understand that, right? Hopefully. All right, so I do have a little bit of a problem though, because now I have got to find the angle that my weight makes relative to my new x-axis. All right, let's see if I can do it. Okay, hopefully I made a convincing argument that the acceleration in the y direction, or y is this new axis, which is perpendicular to the ramp, is going to be 0. So if that's the case, the whole goal is to find a sub x, and that's the acceleration along the ramp. So we look at just the forces as x component, the x component of all my forces, add them all up, and that's going to equal the mass times acceleration in the x direction. So in this case, we have 3 forces, F sub x, plus the x component of the normal force, plus the x component of the weight. I slipped in there. I think the book's got W there, but I just went with F sub g. Okay, so that's my goal. Well, my goal is now to get F. I mean, this is back to chapter 2. I've got some forces here as x component. I've got to go back and find those components. So if I know the magnitudes of the forces, I just take, I've got to take it times like usually cosine. Is that what we do? Cosine theta F plus the normal force, cosine theta N, plus, let's leave this guy as just F sub g for right now, okay? F sub gx. Let's handle these 2 guys. Right, so what are the angles? Should have stayed with that other sheet of paper. I had these drawn. Should have drawn the angles in. I did not do that. Oh well. Whose loss is that? My loss. And sometimes kind of brushed off or so kind of willy-nilly. Always draw your X and Y axes. If you've never done this before on the incline, I always would draw my X, Y axis so you get in the swing of things. That X, Y axis always points in this direction. All right, so here's my mass. And there's my Newton force through the person. Well, what's the angle this 100 Newton force arrow makes with the positive X axis? It's just 0. Theta of F equals 0 degrees. They point in the same direction. It means there's 0 degrees angle between them. And I'll just save myself a little time here and ask myself, regarding the normal force, what's the angle the normal force makes relative to the positive X axis? Push my in there. I want to know that angle. And see if I can squeeze everything in this little top here, it seems like. But I'm going to need some room down here. I probably don't need as much, but oh well. Que sera, que sera. The normal force is perpendicular to the surface, which means that since the positive Y is perpendicular to the positive X, and that's the X's are parallel in the surface, then my normal force makes a 90-degree angle relative to the surface, to the positive X axis. I can go in here and this kind of verifies what I had over here a second ago. Verify exactly this normal force is going to have 0 for a component. So let's put them in here. F cosine 0 degrees plus Fn cosine 90 plus F sub gx equals max. On and cosine 0 degrees. Get your calculator, make sure it's in. It doesn't matter if it's radians or degrees on that one. This guy here is going to be just 1. Cosine 0 is 1, so I just got F. Okay, the elephant in the room has been this guy. Rotating the coordinate system seemed like a great idea. You know, the greatest invention since sliced bread, which, by the way, I believe the sliced bread invention machine came out of Missouri, right next door to my home state of Illinois. You can look that up in your own free time if you like to. But anyway, this guy's always been a little bit of the problem with the rotation of the coordinate system, because now no longer does it, well, it still points straight down, but down no longer is along the y-axis. So we got to break this guy into components. Okay, so we got to find the angle. The weight now is that I'm going to redraw this guy here. It's getting a little messy. Let's make it kind of big here. Let's draw M up here. I'm going to work below it, right? And this is my positive x-axis going up, but I just want to know what angle my weight's going to make relative to the incline. I'm actually going to draw it going the other way. You might think that sounds crazy, but I work on it every time. So here's good old M sub G or mg, my weight. And recall, even though this definitely doesn't look like it anymore, this incline was at theta equals 30 degrees. Where theta equals the angle of the incline, or the angle of inclination. Whatever you like prefer. It's 30 degrees here. It'll vary all over the place. Even though I pick usually very round numbers, and 30 is a great one because sine of 30, I believe, is half. 30 is like 0.86 or something like that. But those are easy ones to keep track of. Cosine 40, blah, 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 blah. I diverge. We all know there's special angles out there. You know, 27.89 is an angle too, but those aren't exactly the ones you always want to work with for ease of numbers. All right, so we'd like to find out this angle right here. make a little triangle. The triangle has components. The hypotenuse is mg. I want to break the mg, the weight, into its components. This is the y side. This is mg sub y. It's the side which is a component along my new y-axis. This side, x, is the component which is parallel to my ramp, which is where my x-axis is. Now I know the positive x-axis went up, but all I gotta do is find that angle and I'm okay. All right, so just bear with me on this. Now I wish I'd not picked my positive x-axis willy-nilly up the hill because it is positive going down, but it wouldn't change the derivation of this thing at all. If you understand it or you don't understand, just if you can accept it, then you'll be fine with what I'm about ready to show you as far as how to get the components of weight, right? And we're interested right now in finding out this, the x component. The y components, well, the y components would have a variant which show me the normal force, which is very important when we hit friction. But right now it had no importance at all other than the fact that offset the normal force, so there'd be no motion in the perpendicular direction to the ramp. All right, now let's just, if you want to just tune me out for a moment, I'm ready to do a proof here. So here we have this angle here, let's call it beta, not B for Brown, but beta is in the second letter of the Greek alphabet, right? And then we're gonna draw this angle right here. That angle right there is we're gonna call that one alpha. Looks like a little fish, or it looks like a funny, badly drawn A. But it's not drawn A and B, let's draw them alphas and betas. And then we make sure, this is a 90-degree triangle right here, which it has to be because this is the y and this is the x side. What do we know? Well, since this is 90, this also is going to be 90 up here. So we know alpha plus beta equals 90 degrees. Okay. But 90-degree triangle too. So beta plus 30 plus 90 are the sum of the interior angles of a triangle. That has to sum up to 180 no matter what. Do a little bit of math here, not much, and you get beta equals 60 degrees. But as alpha plus beta equals 90 degrees, substituting good old 60 for the beta, and we see that alpha equals 30 degrees. Hey, isn't that a coincidence? And it's not. Alpha equals beta equals the angle of the incline, or if we went to the inclination angle, the angle of inclination. I should write it out at least once sloppily as possible. There we go, but I said it. Good heavens. I made up some new letters in the alphabet down there. There we go, a little bit better. So, haha, I now know this angle here, and I know the hypotenuse. It's mg. So if I know the hypotenuse of a right triangle, and I know one of the interior angles, that's not 90, then I can figure out the opposite and adjacent sides. I can break it into components. But here's the problem. Here's the problem. Oh my gosh, this is what happens on this guy. When it comes to the x component for your weight, the thing I wrote up here as mgx here, but fgx up here, that's the x component. The x components are always made by hypotenuse times cosine, right? I think I said way back yonder, that's usually the case, but it doesn't have to be. There's a special case where we're going to deviate from that. And that time has come. mg sine alpha, which equals mg cosine. Yeah, I could write that, but equals, missed the punchline there, mg sine theta. That's fgx. Once again, I invoke the United States Constitution, which says absolutely nothing about this. So about math, there's nothing that says the x component is always the magnitude of a vector times cosine theta. That is true when theta is always drawn from the positive axis. And we like to keep that convention as long as we can. We get used to it. It's a good thing to fall back to. Sometimes though it's not convenient. Here's one where it's not convenient. This angle alpha, which equals this angle theta, is drawn from the hypotenuse to this side right here, which is the y component. It's paralleling the y-axis, the new y-axis. And because of that, well, we still know to get this side here, this is now the opposite side, that sine alpha equals opposite over hypotenuse. Sine alpha, which is really sine theta, equals the x component of weight, FGX, over mg, or mg sine theta equals FGX. Always the case. Always the case. If you want to know the x component for your weight of a mass sitting on a ramp, it's the mass times g, the weight of the mass that's given. It's the weight times sine of the angle of inclination. And the angle of inclination is always given. I mean, if you wanted to go back and use traditional, oh, I want that cosine back, then you got to use this angle. Where's that angle at? Oh, I know where it's at. Look at that. It's up here. And yeah, you can use that angle. No one's going to give you that angle. I mean, it makes so much more sense to say, what's the angle of incline? 30 degrees. This is how much is off horizontal. No one cares about how much is off vertical. I mean, you can, but probably we don't. We want to know how steep of climb I've got ahead of me. And if you tell somebody, hey, you've got a 5 degree, the angle is only 5 degrees on this incline, and you're measured from up here, your incline's like that. You'd better be better off getting a ladder. You wouldn't have to get a ladder out to climb that incline. It just would not work out. And you'd also get very mad at the person. You told me it's a 5 degree incline. Oh, I meant relative to the vertical axis. Oh, we all want to know what is the horizontal. The smaller the number gets, we're used to, oh, that means small incline. Imagine what they do if you have a truck, you see those signs on the interstate, warning 5% grade coming up, but all of a sudden it said warning 85% grade coming up. And if it's measured from the vertical, 85% grade is equivalent to a 5% on the horizontal. Truck drivers would get very nervous. Heck, I would get very nervous if I was approaching that road, definitely. Oh, whimsical incline plane humor. So this is a quirk. This is it in a nutshell. We have got to write it like this, or if you want to, you can go back and write mg cosine. You can't use theta. You got to use the complement of theta. So it's 30. You have to say cosine 60, please. Be a rebel, do it, but do it right. If I catch it wrong and the angle's not there and it's blah, what are you doing? And like, you're gonna kill somebody. But if all the books and stuff like that will use this convention. All right, so I finally have got the ability to write that last equation out now. So I've got my force plus, now you gotta hold that thought for a second. Not quite there yet. Mg sine theta equals max. But I do have to remember, when I have not measured my angle relative to the correct axes, in this case, the positive x-axis going up, I have to sit there long and hard and look at it and say, nah, is that component positive or negative? And if this weight's going down, then the y component is that way, downward, and the x component is down the positive x, or down along the negative x-axis, now down along the ramp. Remember, the positive is going up. So I run over here. You'll never get an inclination angle, bigger than 90. It's always 90 or less. So in other words, sine of any number between 0 and 9 is always going to be positive. So you have to ask yourself, do I almost made up a word there. Do I need to insert a negative sign? And yes, I do. I need to put a negative sign in front of this component here, because if I use this angle theta, which is not measured relative to the positive x-axis, I had to say, you know what? I recognize the fact that it is negative. Taking a Boy Scout oath or something like that. I swear, I know this is going to be a negative number. So what do we got? We have 100 minus, you know, that 50. Good heavens, when I start this problem yesterday, I'm glad it's on video. Give this out every time. I've handled the negative sign, so I don't stick a negative 9 point in here. Sine of 30 equals 50 times AX. AX equals, great, grab a calculator if I fall asleep. It's been so long since I started this problem. 9.8 times 30 sine. And I get AX, drat, it's negative 2.9. I knew it would be because I knew what the answer was initially. So, but I intentionally sabotaged myself. I said you should draw the positive x-axis in the direction of motion if you knew it. I took a guess. I was hoping that person would be able to make it go up the slope. You know, what useless person, what are they doing? They're not doing it. Well, they are slowing it down. It's not going as fast, but they weren't up to the challenge. Or Sean Connery would say, he's not up for the challenge. You can recognize that quote from Sean Connery, all the best to you. Figure out where that's from. And so as AX is less than 0, the mass slides down ramp. Oh. And AY equals 0. That's still, including that a long time ago. Mass does not move along the new y-axis. AX looks suspiciously not. After all that, I'm not going to draw some shoddy little, not even close to being horizontal, paralleling the x-axis. So there, that's pretty good. I like that a lot better. So that's my AX points that way, where I've got a positive X going up and a positive Y. I guess up doesn't mean up along the up the incline, and positive Y being perpendicular to it. So the mass is sliding down, it's not going up or down. Now, if you were concerned and say, hey, you know, wait a minute, way back a long time ago, negative 2.90. I said there'd be a non-zero AX, there'd be a non-zero AY. That's in the old days of the the axes. If we did compute this, we would get AX not being 0. It wouldn't be 2.9. It'd be something smaller than that, but it'd still be non-zero. AY would be something which wasn't 0, but was, you know, between 0 and 2.9. How I can state that is because, ooh, how would I get a net? I would take the square of this guy plus the square of that guy, take the square root of it. And guess what the square root would be? 2.9. Right? So I'm not saying that magically this makes AY, which was non-zero, into 0. Yes, it does, but AX, the new AX picks it up, so to speak. It gets bigger compared to what AX was with the old, what we would have found in the old days. All right. So what other things do I have to say about that? Got a little thing of warning here. So let's put this in summary. Oh my gosh, that's on my sheet of paper. Excellent. Excellent time for summary. And before I draw my desk, which is not my desk, I better not draw on that. I better not make an imprint on it. Oops. What I got? Page 8. Let's take a summary of the incline. The incline plane. All right, so what do we find out about it? The perks. Fewer terms. I lost one term, one whole term doing all that. But like I said, if we throw in friction and you have another person trying to help you pull up the incline, then it's just going to get worse and worse and worse. It's going to have, you're going to keep adding forces or components with every force you add, even with this new system. But unless it's at a crazy angle relative to the incline, those new forces will either be all along the new X or all along the new Y. Now, that's pretty easy to break down components when you know they're like 0, 90, 180, 270s. And there's fewer terms, but also as acceleration is along the ramp. And it's regardless of the system. It was always along the ramp, but the ramp was inclined to the old X and the old Y and the old XY plane. So that meant it had components of both the A and the X and the Y. That was that first table I drew up there, summarizing all those forces. So that's regardless, no matter what. But in the new system, as the X runs along the ramp, AX equals something non-zero, or maybe it is zero. Actually, we use a lot of information when there's a zero. It could be stopped, and we can be trying to figure out the frictional force holding it in place, or maybe there's another person helps out that 100 Newton person. Hey, man, you're having trouble. Let me help you out. And we say, okay, what's the force have to be so that the acceleration is zero? So we just set the acceleration equals zero in the X, and then we solve for the new unknown force of the person, or it's non-zero, like we just found out. But it's something, and no matter what, AY equals zero in this new system, which is a big, big plus. But this isn't just trivial. So useful. We're going to find out this is very useful as it gives the normal force. As it stands, the normal force has to be equal to the Y component of your weight. Now the Y component is going to be, well, if the X component is mg sine theta, then the Y component is going to be point along the negative Y-axis, the new negative Y-axis. So it'd be negative mg cosine theta, and that's the normal force would equal the positive would equal the absolute value of that. When you solve for it, it would equal mg cosine theta. And so big deal. Well, that's neat, but if you've never had physics before, the next step for us to do is to add the frictional force, and the frictional force deals with the value of that normal force. So we have to find that a lot. So those are the perks, okay? But of course, you got to be honest with ourselves. What's the non-perks? What's the bad part about this thing? Weight has a non-zero X and Y components. Up until this point, weight went straight towards zero center, and that was along the negative Y-axis, and it had no X component. We were all happy with that. Now we have to live with this X and Y component stuff, this mg cosine theta, mg sine theta. But all isn't a loss, okay? Because if we have a mass, say on an incline, that's usually what we got. And what else we got here? I mean, this is our incline. It's the whole purpose about doing this thing. And that incline is given by that inclination angle theta. Then the X component of weight, or if you like to, Wx, will always equals mg sine theta. And the Y component will equal mg cosine theta. And these guys here, I have to caution you, because I guess it's a good thing that I did do the axes, the positive X going up. Notice I had to insert a negative sign. If I drew my positive, I read the problem, I drew my positive x going down, then this would just be a positive mg sine theta. So it depends upon which way I drew my axis, which is pretty well standard quo when it comes to status quo. Standard quo? I may have made up a new term. I don't know. Usually, it always depends upon which way we draw the axes, the positive and negative axes. The swapping is going to swap our signs. So these are only the magnitudes. And everyone likes to have some power. You assign positive or negative based on your choice of axes. Is that the plural of axes? We're going to assume it is today. Today it will be the plural of axes. I mean, generally this guy's always going to be negative. We're always going to, I mean, it won't be with the angle of the guy. We'll have to always insert a negative sign. That's because we almost, in every situation I've got, the positive y is always pointing perpendicular to the axis, sorry, perpendicular ramp, yes, but always in a kind of an upward direction this way versus downward. So our weight's hanging downwardish. It still is downward, but it's it's more or less along the negative y-axis. We're going to be figuring out this component, so we always have to stick negative sign in there when we do the sum of the force in the y direction. And that, I believe, is it. Right, so that is the inclined plane in all its glory. Let's do some examples with it now. But not in this video, it's long enough. I gotta edit this thing. Woo. So hope you enjoyed it. Be sure to stick around for the inclined plane sequel called Friction on the Inclined Plane. Oh, I won't give you a hint as far as what's going to happen in that one.